Okay, welcome back to CS580 computer graphics. So this is our second time, actually third time. So until today, we are going to briefly review some of the basics in the computer graphics that actually we already have discussed in the introduction to the course. So last time we discussed the pipeline of the OpenGL, the rasterization, the framework, with some kind of the components of the vertex processor and the fragment processor. And then we're going to also discuss the 3D rotations and the quaternions today. And also the important announcement is that we are not going to have the lecture this Wednesday. So we are going to take a break this Wednesday. So please check out the schedule in our the course webpage. So there is no class this Wednesday. And we're going to resume the lectures next Monday. And then we start to work, discuss some kind of the ideas about the ray tracing next week. Okay. So last time we briefly discussed some of the ideas about like some transformations. So do you remember what are the differences between across these transformations? So yeah, we discussed those kind of details. Basically, the affine transformation was kind of transformations that we are typically applying for many kind of the cases, like having the model view the transformation. And today we're going to discuss more about the ridge transformation, which is basically the rotation, the combination of the rotation and the translation. So ridge transformations are basically one of the very the common the type of the transformations that you can see in many applications. For example, in many graphics the applications, if we consider making some kind of the virtual scene like this, then we probably will basically compose some kind of the 3D models in basically placing those kind of the 3D objects in the virtual scene in a way that we are making some kind of a new scene. And basically like placing all these kind of the objects in the scene would be basically applying some kind of the ridge transformations, basically translating the objects and also rotating the 3D space. So those might be basically one of the way that we are arranging some kind of the objects in the 3D scene with the ridge transformation. And also to make some kind of the animations like this. So when you have some kind of the articulated some 3D characters, typically we're going to have some kind of the skeleton information, basically have some kind of the joint and some kind of the bone information, with some kind of information about like the association between the surface of the objects and also the bones, the points over the bones, in a way that if we apply some kind of the ridge transformation for each of the joint, then we're going to also see some kind of the some animations like this. That basically how each of the parts of the objects are basically moving every time when you basically apply some kind of the ridge transformation for each of the joint. So those might also kind of be one of the applications. And not only in the graphics, but also in the robotics, like the ridge transformation is the common type of the transformation that we can see. So when you basically somehow manipulate some kind of robots to basically interact with some kind of the real objects or the real scene, we will basically need to basically apply some sort of the ridge transformation for each of the joint of some kind of the articulated robots in a way that the end effector of the robot can basically interact with some kind of the real objects. And also in the computer vision, we can see many kind of the applications like utilizing this kind of the ridge transformation. Like one of the kind of the most common sort of the representative example might be the structure from motion. So the structure from motion is basically the case that from the multi-view images, we are basically estimating the pose of each of the cameras, the model view transformation for each of the camera in terms of having some sort of the finding the relative, the translation, the rotation, and all the camera the poses are basically represented as the ridge transformation. So basically, the goal of the structure from motion, the problem is that given a set of the kind of the multiple images, how we can estimate the relative, the rotation, and the translation. So that's basically you might need to basically learn from some kind of the computer vision the courses. And also at the end of all the lectures, we're going to also discuss some neural rendering topics. And also in the neural rendering, basically this structure from motion is the most kind of the fundamental kind of technique. So we basically assume that we are having a set of the multi-view images and also the camera pose information. Then we are basically obtaining this kind of the camera pose information by running some kind of the structure from motion kind of method, which is basically getting this kind of the relative the camera pose information represented as the ridge transformation. So here the question is that how are we gonna basically represent this kind of the ridge transformation? Obviously, like one simple way is to use the matrix form that we discussed last time. So what we discussed last time is that any kind of the affine transformation can be basically represented as a kind of the 4 by 4 matrix, and also with the homogeneous coordinates, right? So if we have the x, y, z coordinates, right? And having the additional the coordinate for the homogeneous coordinates, then any kind of the arbitrary affine transformation can be represented as a kind of the 4 by 4 matrix by having the last row to be 0, 0, 0, 1, right? So when you fill basically any arbitrary 12 the numbers here, that will basically become the one of the affine transformation. And also what you can see is that here basically these three numbers represent the translation, right? So basically, when you just pick any numbers here, those will basically represent the translation. And also, if you basically want to represent some kind of scaling or the sharing, then what we can do is that while we basically making the identity matrix in this like linear part, if we basically change the numbers in the diagonal part, which is basically changing the scaling, right? Or basically, while we basically make this part to be identity matrix, if we change those parts, the non-diagonal the elements, then that will be the case that we are making some kind of the sharing in the transformation. So here the question is that if we want to basically make some kind of the some 3D the rotation, for example, like if we want to rotate some kind of 3D objects along some specific axis with some kind of the angle, then how we can represent such kind of 3D rotation into the matrix form, which is actually not that straightforward, right? So it's, if we want to basically make some kind of rotation along the, for example, like some diagonal the axis with some kind of 45 degree, whatever, then how should we basically change all the numbers in the matrix form in a way that the matrix can represent the desired this rate rotation? So that's basically not the simple way. So today, what we are going to do is that we are going to discuss some kind of the ways to represent these kind of 3D rotations in a kind of the more the compact form. So here the first question is that how many kind of the parameters do we need to represent a 3D rotation? Do you have any guess? So if we want to represent any arbitrary 3D rotation, what would be kind of the minimum number of the parameters? Do you have any guess for that? So please post your answer on this slide. Yeah, so, well, I mean, I'm not sure whether we can represent all the arbitrary 3D rotations with the 2 parameters. But obviously, the minimum number of the parameters to represent any arbitrary 3D rotation is to have the 3 numbers. And the simplest way to basically represent any arbitrary 3D rotations with the 3 numbers is to use the Euler angles that we actually briefly discussed last time. So the Euler angle is basically the angle, which is basically the representation introduced by the that Euler, who is famous with the Eulerian the path idea with the 70 bridges in the city, like finding some kind of the path that is like passing the bridge like only one time. So he is basically the Swiss mathematician in 18th century who was basically introducing many kind of the interesting ideas about like representing all these rotation kind of things. So we're gonna see what he has done in terms of the representation of the 3D rotations today. So the simplest idea in terms like describing any kind of 3D rotation is to basically have some kind of 3 numbers along each of the x, y, z axis. So basically, as we have seen in the last lecture, what you can do is that for each of the x, y, z axis, we can basically have some kind of the rotation angles for each of the axes. And then we can sequentially apply those kind of the 3 rotations. So that can be simplest way to represent all these 3D rotations. And actually, this way can basically cover all the possible 3D rotations. So that's kind of the interesting. And this idea, so like, having the angles for this 3D rotation was actually first introduced to basically control some kind of the flight of the aircraft. So, actually those kind of 3 angles were basically called the pitch, yaw, and the roll. So here basically pitch is the angle basically controlling like either lifting or like lowering the aircraft, and the roll is basically the angle basically to control the rolling on the left and the right like this. And also the yaw is basically the angle that is controlling the direction that the aircraft is basically heading to. So basically these are basically three terms to represent the three angles, especially in terms of like controlling the flight of the aircraft. And this kind of the idea, like having these three angles to represent the 3D rotation, has been used in the many applications. So I'm not sure whether you have seen this kind of the camera destabilizer. Have you seen those kind of things? So this is kind of the stabilizer of the camera in terms of making some kind of the smooth trajectory when you basically shoot some kind of the video using the camera. And you can see that actually those kind of the some devices have this kind of the gimbal, which is some kind of the hardware implementations of the older the angle. So as you can see, we are having these three rings, and each of these rings are basically making some kind of the rotations for each of the axes in a way that we can make any kind of arbitrary 3D rotations. So this kind of the gimbal actually can be seen in kind of the many kind of the some hardware devices. So this is really some kind of hardware implementations of the older the angle. And as you can see, and also the order, like applying this kind of the rotations, 3D rotations, are basically making some kind of the differences, right? Because the 3D rotations are basically not commutative, which means that if you apply the rotations in the order of the x and the y and the z, or if you apply the same rotations in the order of the z and the y and the x, those two will basically make some kind of the different outputs, right? So the order is really important. And there are kind of multiple ways to basically define this kind of the order, or like applying these 3D rotations. Let me move to the next slide. Yeah. So depending on the order that we are applying this kind of the rotations, actually there are some kind of the lots of the combinations. So even you don't need to apply the rotations along the three axes. So you can just like repeat applying the rotations along the same axis, but still all these cases are basically the cases that we can cover all the possible 3D rotations. But the interesting kind of thing in terms of this kind of the hardware, the implementations of the order the angles is that there are some kind of the limitations, which is called the gimbal lock. So what's the kind of the problem of the gimbal lock? So basically the idea is that we are having these three numbers to represent all the possible 3D rotations, right? So which means that if we fix one of those kind of the parameters, then we will still have the 2 degrees of the freedom, right? We can still basically cover like the 2 degrees of the freedom of the rotations. But some kind of the special situation is that if we somehow set the number for each of the one of the 3D parameters, actually then we can see some kind of the cases that actually the two other the rotation the parameters play the same role, which means that we are not only losing like 1 degree of the freedom, but actually we are losing 2 degrees of freedom by only setting the one of the parameters. So that's kind of interesting the cases. So let me show a video what this means.
So how does Euler work? This gimbal machine shows us. Each part is linked to one another, so when the parts slide around, we can see how the rotations are passed on. By spinning each of the machine's 3 arms, we can rotate the jet into any angle. But notice, when the jet points up, how 2 of the circular arms match up. This is exactly the same effect of gimbal lock, causing 2 circular arms to rotate on the same plane.
So yeah, as you can see here, the problem is that actually we originally had some kind of 3 numbers, like making all the possible like these 3D rotations, which means that if we fix like one of the 3 numbers, then we're gonna still have the 2 more the numbers that we can control, right? But in some specialty cases, like when you basically set some kind of the number for one of those parameters, in this kind of specialty cases, the rest of the 2 numbers will play the same role, basically making the same rotations, which means that while we basically set one of the numbers, we are losing not only one of the degree of the freedom, but we are losing actually the 2 degree of the freedom. So that's kind of the problem that is called the gimbal lock. So depending on how we define the gimbal, actually there are such kind of the cases that we can easily basically lose like 2 degrees of the freedom by basically setting like one of the numbers. So if we see this kind of the such kind of the cases, like the neural deformation, this is like one of the examples. So this is the case that we are having this kind of the XYZ model, which means that we are basically applying the rotation along the Z-axis first, and then the Y-axis, and then the X-axis. So in this case, if we find the cases of the gimbal lock, so what we can do is that if we set the 90-degree of the rotation along the Y-axis here, that what you can see is that we end up seeing this kind of the rotation. As you can see here, the rotation along the x-axis and the rotation along the z-axis is making the same rotations. So this is one of the examples that we are losing 2 degrees of freedom by basically setting one number of these three parameters. Is this clear? Any questions on this? So any questions? If you don't have any questions, one of the questions that I have is that, so now we are seeing this form of the 3D rotation, right? And can you guess what will be kind of the axis of the rotation, like this final rotation? So now when you basically control one of those the two numbers, what will be kind of the rotations along which axis that we're gonna see? Yes. So yeah, I recommend you to play with this kind of some 3D rotations with some bunch of the cases. Yeah, it looks like rotation along some specific axis like z-axis, y-axis, and the x-axis. Actually, the answer is that the rotation of this matrix is not that simple the rotation. So if you want to check what will be kind of the rotation that we're gonna see using this kind of the matrix, I just posted the link, which is basically the kind of the website you can convert any representation of the rotations into the other form. So check yourself, go to this website and see for any kind of arbitrary the alpha and the gamma, what will be kind of the rotations that we're gonna see. So actually the thing is that while this matrix looks simple, actually the rotation that we are making with this rotation is not that kind of simple rotation. So this is kind of thing. So that's kind of thing. So we can see this kind of the gimbal of the cases with all of the angles. And also kind of thing is that while this kind of the Euler angle the representation looks kind of like intuitive, okay, there are kind of the many cases. Let's say like, for example, we want to make some kind of the compositions of the 3D rotations. So we have the rotation along the y-axis with the 90 degree, and also after that we also want to apply the rotation along the x-axis with the 90 degree. Then what will be kind of the final the output of the composition of these two rotations? Well, obviously it's not some kind of like simple the arithmetics, like just adding these two angles. Like so we are not actually getting the 180 degree of the rotations at the end by combining these two. But interestingly, like if we combine these two rotations, then we're gonna actually see the rotation, which is making the rotation along the diagonal of the axis with the 120 degree. So these are basically some kind of the some complicated things in terms of how we're gonna easily see that when we combine some rotations, what will be kind of the final rotations that we're gonna see. So in terms of like doing this kind of the calculation, actually the Euler angle is not the kind of the best, the intuitive representation. So that's basically what we are going to discuss some kind of the other representation, which is especially good for this kind of the some composition of the rotations. So that's basically the idea of the quaternions that we're gonna mainly discuss today. So at this point, before we move on to the quaternions, do you have any questions for the Euler angles? Is everything clear? So yeah, feel free to leave some questions both on the Zoom chat or the Slack. So especially if you leave some questions on the Slack, then it's easier for me to follow up all the questions even after the lecture. So let's go for that. And then, yeah, so let's then move on to the quaternions. So actually, we want to find some kind of some representations for the 3D rotations, which is especially good for some kind of some compositions. And then before we actually discuss some kind of 3D rotations, let's briefly discuss some of the cases of the 2D rotations. So for the 2D rotations, we're gonna also briefly see the idea of the Euler's formula, the same Euler here as well, the Swiss best rotation. So basically, what we are going to see is that let's think about the space, the 2D space of the complex number. So we are having the real number, the axis here, and also the imaginary the axis here. So having this kind of the two the axis. And what we can see is that any kind of the point over this 2D plane is basically representing like one complex number, right? So this is clear. And we're gonna also draw a kind of unit circle over this kind of the 2D space. Then what we can see is that any point over the circle is basically corresponding to the one 2D rotation, right? Because if we pick any kind of the point over the circle, then we can see the rotation, the angle from here to this kind of. So that's the thing. Like you can say that like any of the point over the circle is basically corresponding to the 2D rotation. And what you can see is that basically any point over the circle is basically having this kind of form of the complex number, right? This is simple. Like we are basically having the real number, the axis as kind of the x-axis, and also the imaginary number is kind of the y-axis. So basically, when you add these two, basically we are having the complex number, which is basically indicating one of the point over the 2D circle. Okay. And what the Euler's formula says is that actually this point, this complex number, the cosine pi plus the I sine pi, actually can have this form. So these two are basically exactly the same. It's kind of the interesting part that this kind of the complex number represented with the trigonometric functions actually can be rewritten with the exponential form. I guess this is like most of you learn some kind of the parts of your some kind of the math courses before, right? So yeah, so these are basically the Euler's formula. So you can also quickly see like how we get this kind of the results. Basically, this is kind of there are actually multiple ways to prove this. One of the ways to basically having the Taylor's expansion for the exponential form. And if you rewrite everything kind of in this way, then you can see that actually this exponential form becomes the same with the cosine the x plus the I sine x. So this is the Euler's formula. And from the Euler's formula, actually what we can see is that now, if I go back to the previous slide. So what this means is that every 2D rotation now can be represented into this form of the exponential, right? Every 2D rotation with the angle of the pi now also can be represented into this form. So there's some kind of the correspondence between the 2D rotation with this kind of exponential form. So we can say that this is kind of one of the ways that we are representing the 2D rotation. And also what we can say is that if we multiply these two of these kind of the exponential forms, that becomes the combinations of the 2D rotations, right? Because so as we can see here, if we multiply the unit the complexity numbers, that becomes like some kind of another complex number, which is also the unit complex number and also representing the combinations of the 2D rotations, because that will result in the case that we are adding the two rotation angles. So this is like that useful effect, but we're gonna see like how this can be extended in this reading case. But this is like something that you need to keep in mind, that we are basically having some kind of the form of the complex numbers that has these properties. Like the multiplication of like these two complex numbers becomes the complex number which is corresponding to the combinations of the 2D rotations. So this is kind of the interesting effect that we are going to see. Any questions on this? So then the question is that how we can find such kind of things for the 3D rotations. So like the question that some mathematicians in the 19th century had for regarding this kind of thing was that, so yeah, we can see that if we have this kind of the 2D space of the complex numbers, we can have this kind of the present some kind of the correspondences in terms of the multiplications of the complex, the unit complex numbers becomes the combinations of the 2D rotations. Then the question is that, can we also find some kind of the 3D space where the points over the unit sphere correspond to the 3D rotations, and also their multiplication corresponds to the combinations of the 3D rotations? Can you see this kind of extension? So that's what the mathematicians do, like finding this kind of generalization, right? So this was kind of the question that people had in the 19th century. And all the mathematicians basically have some kind of the difficulties, like having this kind of some 3D case. And what the William de Hamilton found in the 1843 was basically the fact that actually we need not the 3D space, but actually 4D space to have see this kind of the relationship between the complex number and the 3D rotations. So basically, we are now having some kind of mapping of the 4D, the unit sphere in the 4D space to the 3D rotation. So that was kind of the some kind of discovery by the Hamilton. He was kind of the mathematician, Irish mathematician, the island, and he basically found this kind of the came up with this kind of the idea on the way that here basically heading to the kind of some Royal the Irish the economy on the Royal the Canal. So what you can find is that if you have any chance to go to the Dublin in over the Royal the Canal on the bridge, you can see this kind of some sort of the stone the plaque, which is basically saying this kind of thing. To the next slide. Yeah. So if you go to the Dublin, then you can find this kind of stone plaque, which is basically sort of like celebrating this kind of discovery by the Hamilton, discovery of the Quaternions. Genius idea discovered that the fundamental formula with Quaternion. Yeah. So that's basically why we are calling this as kind of Quaternion, because now we are not having the 3-dimensional space, but the 4-dimensional space to represent the 3D rotation. This was kind of the very interesting ideas in terms of like extending the oldest formula into the 4D case for the 3D the rotations. So yeah, if you have any chance to go to the Dublin and just find this kind of stone plaque and just like take a photo, so you see. So yeah, this is kind of also the book that he introduced the idea of the quaternion at the first time. So we're gonna briefly see what's the kind of the meaning of the quaternion, how it is basically defined, and also how it is basically related to the 3D rotation. So let's briefly go over with some kind of the very much the basics of the quaternions. So quaternion is basically the case that now we are having the one real number and then 3 imaginary numbers. Yeah, actually the mathematicians basically were finding some kind of all the combinations, like having like one real number and the 2 complex number, the 2 imaginary numbers, and 2 real numbers and like 1 imaginary number, like all the combinations. But all the combinations in the 3D space was not really working in terms of finding the mapping to the 3D rotations. And the answer was that actually we need the 4-dimensional space with the 1 real number the axis and 3 the imaginary the number the axis. So let's think about this kind of the new types of the complex number, having the 1 real number and 3 imaginary numbers. So now we are having even 3 different types of the imaginary numbers, I, J, and the K. And since all these are the imaginary numbers, they basically satisfy this constraint. The square of like each of the imaginary number becomes the -1. And additionally, they are having this property. I times J is K. J times K is I. And also K times I is A, having this kind of property. And also here, the key thing is that the multiplication is not commutative, which means that when the I times J is K, J times I is not K. So having this kind of like non-commutative property is actually one of the essential the property to find the mapping to this radial rotation set. So here the question is that so if the multiplication is not commutative, when you know that I times j is k and j times k is I and it's k times I is j, what should be the j times I? So let's find the answer of this. Yeah, so some of you might just like remember what the answer is, but you can actually also derive the question in multiple ways. So if you just like derive all the kind of things, then you can say that actually j times I becomes the minus k. So check this out yourself. So we are having like all those kind of the properties that these are some kind of the essential the properties of the quaternions. Like all this curve, each of the images, the numbers becomes the minus one. And I times j becomes k, j times k becomes I, and k times I becomes j, and the other way around, like j times I becomes minus k, and k times j becomes minus I, and also the same. And also the multiplication, like all the three images in the numbers becomes the minus one. This is coming from the previous two conditions. So this is clear, right? And we're gonna also briefly see some kind of the terminology with the quaternions. So we can first define the norm. So the norm of the quaternion can be defined in the same way with the vector. So when you basically think like we are having the four-dimensional vector, the norm of the quaternion becomes the L2 norm of the vector like this. So this is the norm of the quaternion. And we can also, as we define the conjugate for the typical the complex number, we can also define the conjugate for the quaternion as well, which is the case that we are taking the minus for all the imaginary numbers. Right? And what we can see is that the multiplication of the quaternion Q with each the conjugate the Q bar becomes the security norm of the quaternion like this. So this is very clear. You can calculate this yourself, and you can see that actually the multiplication between these two becomes the squared norm of the quaternion. And also we can define the inverse. So inverse is basically a kind of the quaternion, which basically results in that the multiplication with the original the quaternion becomes the one, right? For the other way around as well. If we find this kind of the quaternion, that becomes some sort of the normalized the conjugate of the quaternion. So this means that if the quaternion is the unique quaternion, where the norm of the quaternion becomes the one, then the conjugate becomes the same with inverse of the quaternion. So for the cases when we have the unique quaternion, the conjugate becomes the same with the inverse of the quaternion. And as you know, we see like this kind of properties for the matrix demultiplication. Actually, what we can also see is that the conjugate and the inverse of the product becomes the product of the conjugate and the inverse, but in the reverse order. So we can also see this kind of things for the inverse of the matrix and also the multiplication. So it's kind of the same in the quaternion case as well. So if you take the conjugate and inverse of the product of the quaternions, that actually becomes the product of the conjugate and the inverse, but in the reverse order. So those are kind of the properties that we can see. So these are basically all the things that we can derive from the properties, the essential properties that we discussed in the previous slide. Any questions on this? So yeah, we're gonna quickly also see another kind of the term, which is the conjugation. So conjugation is basically different with the conjugate. So conjugation is kind of the operation defined by a kind of the quaternion, which is also applied to the another quaternion. So when you talk about like the conjugation of the P by Q, which is basically making some kind of the operation with the quaternion the Q, which is now applied to the quaternion the P. So again, this basically means that conjugation of the P by Q means that we are basically making the conjugation the operation with the Q, making this kind of the CQ the operation, which is operate to the which is basically applied to the the other the quaternion P here. So you can see that this operation has this form. Basically, if you multiply the quaternion Q and its conjugate on the left side and the right hand side, then it becomes this some kind of operation of the conjugation. And the reason actually why we are seeing this like the conjugation, the operation is that we're gonna see the reason. Also, one kind of thing is that while this is kind of the multiplication, like the two quaternions on the left side and the right hand side like this, actually this operation actually can be represented as kind of the linear function, which means that if you have this kind of like given the quaternion dq, which is having this form, if you make this kind of the 4x4 matrix, then when you also represent the quaternion the P into a kind of the vector form here, if you multiply this kind of a matrix, that becomes kind of the output of the conjugation. So you can see how we can derive this kind of the matrix from the definition of the conjugation here. So it is clear. So while we define the conjugation the operation like this, actually like having this kind of the multiplication of the quaternion can be the same as kind of like we are defining this kind of the 4x4 matrix and having the vector form of the quaternion and doing some kind of the multiplication to get the final the outputs, and that becomes the same operation as this. So basically this conjugation operation defined with some kind of the specific the quaternion the Q can have some this kind of the linear function, linear map default. And the interesting thing is that this conjugation the operation has many kind of the interesting the properties. So this is kind of the main part for me. So what we can see is that if we see the norm of each of the column of this kind of the matrix, then you can see that the norm of every row and also the every column becomes the square root of the norm for the input the quaternion the Q. And also what we can see is that all the rows and also all the columns are orthogonal to each other. And also if we compute the determinant of the entire 4x4 the matrix, then the determinant becomes the 8 times of the norm of the input the quaternion becomes this. Then can you see some kind of the some relationship from this to the 3D rotation? So here basically what we can see is that if we have the input the quaternion Q, which is defined this conjugation as kind of the unique quaternion. So let's say that the norm of this Q, the quaternion becomes the 1. Then what we can see is that the norm of each of the row and column becomes 1, right? And all the rows and the columns are orthogonal to each other. And the determinants also becomes 1, right? For the unique quaternion, the case. Then if we only see this part of the matrix, so it will be also the same. And because like here the parts of basically 0, 0, 0 and also the 0, 0, 0. From this, what we can see is that each of the row and the column will have the norm of each of the row and the column will be 1, and all the rows and the columns will be orthogonal to each other, and also the determinant will be 1. This means that this part of this kind of 4x4 matrix will correspond to any of the 3D rotation. So these are basically the properties of the 3D rotation, right? The matrix of the 3D rotation has the property that each of the norm of the rows and the columns becomes the 1, and also the determinants is also the 1, and all the rows and the columns are basically also not each other. So from this kind of the linear map, kind of the formulation of the conjugation, the operation for the unit quaternion, we can see this kind of some kind of the correspondence between each of the unit quaternion and also the 3D rotation by having this kind of the conjugation the operation. So this is kind of the way that we can find some kind of the mapping between the unit quaternions and the 3D rotations. It is clear. Any questions on this? Let me know if you have any questions. Yeah, so this is kind of the operation that we can see some kind of the mapping between the unique quaternion and the 3D rotation. Then some kind of the analogy that we can see with the Euler's formula for the 2D case is that also in the 2D case, what we could see is that the unit the complex number in the two-dimensional the complex space was corresponding to the 2D rotation, right? So now what we can see is that in this kind of the four-dimensional space, the unit quaternion is basically corresponding to the each of the 3D rotation, right? So this is like one similar thing. So also in the 2D case, we just need to draw the unit circle, and one of the points there was corresponding to the 2D rotation. And also for the 3D case, now we are thinking about some sort of the imaginary, some sort of the 4D-dimensional the sphere, which is called the 3D sphere. Actually, you can see that the 3D sphere basically means some kind of some hypersphere in the 4D-dimensional space. And any point over the hypersphere in the 4D-dimensional space is actually now corresponding to the 3D rotation. And also the thing is that we also could see that the multiplication of the two, the unit, the complex number was basically representing the combination of the 2D rotations. And what we can also see without the proof here is that if you also multiply the two unit quaternion, then you can see that actually there is this kind of property. So if you basically compute the multiplication of the two unit quaternion and take the conjugation, this becomes the same as basically you first take the conjugation, the linear mapping the function, and then multiplying these two. So you can, from the definition of the conjugation in the previous slide, you can check this yourself. So I'm just like omitting the proof. But from this definition, actually you can check that the product of the quaternion and taking the conjugation is actually the same as basically taking the conjugation, the 4x4 matrix from each of the unit quaternion and taking the product of these two. And from this product, since we also see that each of the this 4x4 matrix coming from the conjugation is also corresponding to the 3D rotation. What we can see is that the multiplication of the unit quaternion is also corresponding to the combination of the 3D rotations. So this is also the same with the 2D case. So this is basically what we wanted to find in the 3D rotation case. So in the 2D case, we had this kind of representation that the multiplication is corresponding to the combination of the 2D rotations. We are also seeing the same case. The multiplication of the unit quaternion is corresponding to the combination of the 3D rotations. Is this clear? So I recommend you to check this out, whether this is true or not. And also the other thing is that these are the cases that we are having this kind of complex number, where the real number parts becomes the cosine of the pi. So when the 2D rotation is represented with the angle of the pi, the real number part becomes the cosine pi, and the imaginary number becomes the I times the sine pi. So we are having this kind of two numbers in the 2D rotation case. And then what we can see in the 3D case is that also the real number parts becomes the cosine of not the theta, but the half of the theta. So when the rotation is basically having the angle of the theta along the axis, the vector u. What we can see is that the real number parts becomes the cosine of the half of the theta. So this is the difference. So we are not just having the cosine theta is the real number of the parts, but we are having the cosine of the half of the theta is the real number of the parts. And also the norm of the imaginary parts, the coefficients of the imaginary parts, the norm of those kind of coefficients becomes the sine of the half of the theta. So that's kind of the analogy with the 2D case. But the thing is that we are not having the theta, but the half of the theta here as well. And also the coefficients of the 3D imaginary numbers also represent the axis of the 3D rotation. So that's kind of the analogy between the 2D and the 3D case. Interesting. So you might be wondering like how we can basically derive this kind of results, like how we can see that from the unique quaternion, how we can see this kind of correspondence with the angle axis representation of the 3D rotation. So actually, one way that we can also represent the 3D rotation is to just have the having the axis of the rotation and also the angle. So when you also want to know the axis of the rotation and also the angle of the rotation from the unique quaternion, we can find those kind of axis and the angle in this way. And the question might be is that how we can derive this kind of the mapping from the unique quaternion to the axis and the angle. And there can be some multiple ways to this. So I'm going to skip some of the details here. You can also check out some of the more details in the slides. But one of the ways that we can check this out is basically using the Rodriguez formula. The Holland Logli is also the French mathematician was also working on those kind of things. And the Rodriguez and Euler, those two people were basically the people who were basically deriving all these kind of formulations in the 19th century. So you can check this out. So in the Euler and the Logli formula, what we can say is that let's think about that we are making the rotation along the univector decay with the angle theta. So here the first question is that when you want to make some kind of 3D rotation with the axis k with the angle theta, rotating the vector v with the rotation of the axis k and theta, how we can represent this rotation having this kind of the axis k and the theta into the 3x3 matrix form. So this is like all about the Rodriguez formula. So you can basically check out those details later. But briefly, what we are doing here is that for the given the vector v, we can decompose this vector v into the part which is parallel to the vector k, and then the part which is orthogonal to the vector k. So given any kind of the arbitrary vector v, we are decomposing this into the two parts. Like one is parallel to the axis k, and the other one is basically orthogonal to the axis k. But then what we can simply see is that the parallel part does not need to rotate because this vector is already parallel to the rotating axis. So we can keep this part. We only need to apply the rotation for the part which is orthogonal to the rotation of the axis. Then what we can also see is that the vector which is orthogonal to the rotation of the axis k is basically just a matter of applying the 2D rotation, right? So in this kind of the plane, which is basically orthogonal to the the rotation of the axis k, basically taking the axis k as kind of the normal. So in this kind of the 2D plane, we can apply the 2D rotations for this kind of the orthogonal part of the vector plane. So these are all the conditions about this. So we keep the parallel part and applying the 2D rotations for the orthogonal part. Then you can basically derive all the formulation. Here's like one small detail is that this is kind of the notation that we are representing the cross product as kind of the matrix form. So when you basically having like the two 3-dimensional vectors, like having the cross product, actually this kind of operation actually can be rewritten by just taking a kind of the matrix form, rewriting this vector and the cross product into the 3x3 matrix form. So this is representing, replacing this kind of the cross product into the 3x3 matrix, making some kind of skew symmetric matrix. You can check out some details later. So from basically this kind of formulation, what we can say is that given the rotation, the axis k and the angle theta, we can derive this kind of the matrix form, 3x3 matrix form of the rotation, which is basically derived from the rotation of the axis k and the rotation of the axis theta. Check this out yourself later. And what we can also see is that if we have some kind of the unique quaternion with the A plus B, I plus C, J plus BK, when you have this kind of the unique quaternion representing a 3D rotation, the conjugation the operation also basically mapped this quaternion to this kind of 3x3 matrix, right? This is exactly coming from the previous slide. So, and these two should be identical, right? So here the question is that how we can find the rotation the axis k and also the theta that makes these two matrices to be the same. These are all these kind of some simple calculation. So yeah, you can check yourself. So what you can see is that if we just make this the sum of the diagonal term to be the same for those and these two matrices. So the sum of the diagonal term should be the same, right? So if you check this out, then you can see that the A should be cosine of the half of the theta. Also, basically take the sum of the some parts of the diagonal term, then you can say that the B should be this, and also C and D should be those kind of things. So from this kind of the formulation, we can see that when you have the, so these are some kind of details, but so when you have the, here, basically having this kind of the, unique quaternion with the coefficients of A, B, C, and D, then we can directly derive the rotation axis and the angle like this. So these are all good, right? Any questions on this? Yeah, so I'm skipping some details, but you can also check out those details in our the slides. I already posted the slides on the course web page. Okay, check this one. So from this, also what we can see is that you now can see how we can convert across the multiple the representations. So given the like the Euler the angle, actually it's easy to see how we can convert this into some kind of three by three the matrix, right? And also from the unique quaternion, we can also convert this unique quaternion to 3 by 3 matrix, right? This conversion should be easy. And also from the unique quaternion, we can also convert this into the axis and the angle form, right? So we can do all kind of conversion across the all different representations of these three rotations. So yeah, so we check out this kind of the way that we are so yeah, making some kind of some convergence across the different representations of these three rotations. Any questions on this? So here actually also the interesting question is that is the mapping from the unique quaternion to the 3D rotations is the surjective? Is it the onto mapping, which means that for any kind of the arbitrary 3D rotation, does it exist? I mean, can you find some kind of the unique quaternion that represents any arbitrary 3D rotation? Is the onto relationship? Yes, actually this is true. So for any kind of the arbitrary 3D rotation, you can find any kind of unique quaternion that satisfies this kind of the this relationship. Yeah. So if you have any kind of 3D rotation with the arbitrary axis and the angle, you can always find some kind of unique quaternion that is corresponding to 3D rotation, which means that the mapping from the unique quaternion, to the 3D rotation has the surjective mapping. There always exists a unique quaternion that is basically mapping to the arbitrary discrete rotation. For any arbitrary discrete rotation, we can find the unique quaternion. And the other question is that, is this mapping the one-to-one mapping? Is also the injective? So we know that for any arbitrary discrete rotation, there should exist one or the many unique quaternion, right? But then the question is that, is the quaternion is there like only one single quaternion, or there can be some multiple quaternions to the 3D rotation? So here the answer is that actually there exist always two distinct unique quaternions that corresponds to the 3D rotation. The thing is that if we see that the unique quaternion Q is corresponding to some specific 3D rotation, which is represented as the R, then we can say that actually the minus Q is another the unique quaternion that is also corresponding to the same 3D rotation. So that's kind of thing. So if you basically derive all the things, then you can see that actually when the Q represent the rotation of the axis of the U and the angle d theta, then actually the minus Q becomes a unique quaternion that represents the rotation with the rotation the axis with the minus u and the 2 pi minus theta. So whether you have like rotating like this along this way and flipping the rotation the axis and then rotating along the 2 minus the theta degree, the angle, and these two becomes exactly the same. Rotating along this axis with the pi, and rotating along this axis with the 2 pi minus the theta becomes the same rotation, right? So this is kind of like interesting fact. There always exist two distinct quaternions, unique quaternions that represent the same rotation. So this basically means that there are some interesting the 2-to-1 mapping between the unique quaternion and these radial rotations. And we know that basically the unit quaternion is basically some kind of the points over the unit hypersphere in the 4-dimensional space. So we can also see that there are some basically 2-to-1 mapping between the points over the 4-dimensional sphere, the unit sphere, to the 3D rotations. And especially the opposite points, two antipodes, the opposite points over the 4D rotation, 4D sphere, sorry, the 4D, some imaginary 4D sphere are basically corresponding to the 3D rotation. It is clear? So yeah, some kind of the interesting mapping. So if you basically make some kind of the cut of this sphere, then you can see this kind of automatic. But so you should be careful because like on the border of this kind of the cut, you will also have the 2 points. So it's kind of the complicated. So basically, we are having this kind of the 2-to-1 mapping between the 4D-dimensional the unit sphere with the 3D rotations. This was the very interesting finding by the Hamilton with the quaternions. Any questions on this? Okay. So if there is no question, then let me ask some question and see whether you have some understanding of this. So in the previous slide, we have seen that the rotation along the y-axis with the 90-degree and the followed by the rotation of along the x-axis with the 90-degree actually becomes the same with the rotation along the diagonal of the axis with the 120-degree rotations. Right? Can we check whether these two are actually the same using the quaternions? So let's check. So you can basically calculate the combinations of the two rotations using the quaternion and see whether that quaternion is the same way the quaternion representing this rotation. So let's check this, and please post your answer on this slide. So we have enough time, so I'm gonna give you 5 minutes to work on this. Yeah, maybe you can check out the answer. Yeah, I'll also post the solution later, but actually, yeah, you can just quickly compute all the kind of the quaternions, the multiplying the two quaternions and see. Let me show. Yeah, you can you see my slide? Yeah, you can check out the multiplication of the two quaternions and see whether these two are the same with the quaternion of the 120 degree of the rotations. Cool. So those are kind of things. So let me also quickly go over some kind of the more the properties of the quaternions. The first question might be is that given a unique quaternion of this, which is corresponding to the some specific rotation, with the rotation 3D rotation the R here. If we take the conjugate of the quaternion, or this is the unique quaternion, so the conjugate should be the same with the inverse of the quaternion. Then what does this kind of the conjugate or inverse of the unique quaternion represent in terms of video rotation? Any guess on this? No, this is question 5 for DTA. Can you even see my slide? No? So if I'm asking this question, so given a unique quaternion, when you know that this quaternion is corresponding to this 3D rotation R, if we take the conjugate or the inverse of the quaternion, then what does this kind of the inverse or the conjugate represent the which 3D rotation? So it's basically flipping the axis of the rotation. If you see some kind of relationship with axis and the angle, you can see that the conjugate or inverse of the unique quaternion is flipping the rotation axis, so which means that it now represents also the inverse of the rotation, right? So it's basically simple. The inverse of the unique quaternion represents the inverse of the rotation. And given the two rotations represented with the two unique quaternions of the QG and the Q1, then how can you also represent the relative rotation from the Q0 to the Q1? So what we can see is that, let's say the R0 is basically the rotation, 3D rotation corresponding to the Q0, and the R1 is the 3D rotation represented to the 3D, corresponding to the Q1. So let's say this R0 and the R1, these are the 3D matrices representing the rotations. Then the relative rotation of these kind of the matrices will be represented as the R0 inverse times the R1, right? So it's the same. So when you take the represent the relative rotation from all those the properties, we can say that also the relative rotation can be represented into the Quaternion form as kind of the Q0 inverse times Q1. This is clear, right? So the inverse of the quaternion is corresponding to the inverse of the rotation, and also the multiplication of the quaternion is corresponding to the multiplication of the 3D rotation the matrices, right? And also the other thing is that, so when a unique quaternion Q corresponds to the rotation with the axis A and the theta, somehow if we can define the, sort of the square root of the quaternion, Q to the 0.5, then what does the this rotation, this quaternion represent as 3D rotation? Because what we can say is that somehow if we can have this quaternion Q to the, then if we multiply this twice, then this should be Q, right? Which is becoming this rotation. So which means that the sort of the square root of the quaternion should represent the halfway of the rotation. Kind of clear. I think it's without some kind of proof. But what you can see is that basically the sort of the square root of the quaternion should represent the halfway of the kind of rotations with the half of the angle while having the same axis. You can also check this out basically in some kind of more the definitions. So we can also generalize this fact. So in terms of if we have the QT, this will be the case that we are having the rotation of the R with the same axis with the T times the theta. Okay. Is everything clear? So from this, what we can see is that, so actually as kind of one of the applications of all these kind of 3D rotations and the rigid transformation, one of the application was making some kind of animation, right? So let's say we have the rotation of the R0, let's say like 3x3 matrix, and also the R1. We want to interpolate between these two 3D rotations, which also has the corresponding rotation, the quaternion Q0, and also the corresponding quaternion Q1. And we want to smoothly interpolate between these two rotations. That is kind of very essential things when you want to make some kind of this animations, moving the camera or moving some kind of the objects or moving the joint, some articulated objects. Then how can you make this kind of the interpolation? So what we can see is that the relative rotation from the Q0 to Q1 can be represented in the previous slide. In the previous slide, what you can see is that the relative rotation can be represented as this. So what this means is that we can interpolate between these two rotations by starting from the Q0 and applying this relative rotation while varying this T. So we are basically making the quaternion the power of the T, while basically varying this T to be 0 to 1. So by taking this kind of the computation, we can interpolate the 3D rotations with the quaternion form. So that's kind of also kind of easiest way. I mean, one of the applications of the quaternion that can be also used for some kind of the interpolation of the 3D rotations. And also here the question might be is that then how can he compute the power of the unit quaternion, right? So given this kind of the fact, when you have the Q to the T, the power of the quaternion, how can you compute this? Well, actually computing this can be done kind of the opposite way, because we know that Q to the T should represent this rotation. So this will be the case that we are having the axis of the A and also the angle of the T times theta, right? So if we know the axis and the angle, then the other way we can compute the unit quaternion corresponding to this rotation. So this can be actually the way that we can easily compute the Q to the T. And once we have the way that we can compute the Q to the T, then we can interpolate these two 3D rotations by having these kind of the formulations. Make sense? And also one more interesting fact is that if we do this kind of interpolation with the quaternions, actually that becomes exactly the same as kind of like we are interpolating over the four-dimensional sphere of the unit quaternion with some kind of the constant angle. So this kind of the interpolation over the sphere is often called the slope, spherical linear interpolation. So if we take the slope, spherical linear interpolation, interpolating over the four-dimensional sphere with the constant angle, starting from the Q0, representing the sort of the initial rotation, and the Q1 to the target rotation. So if we take the spherical interpolation over the four-dimensional space, actually this kind of interpolation with the constant angle becomes exactly the same, having this computation. So I'm not gonna provide all the proof for this because it will take another 30 minutes. You can, if you are interested in some more details, then you can check out those kind of things in some many kind of the articles on the online. And this, I posted a link on this lab, but this is like one of the kind of the material that you can check out this kind of relationship. Using the Quaternion, you can also compute this kind of the 3D, the interpolation of the 3D rotations. And you can also check out these are all the identical some kind of the formulations for the same the interpolations. And one quick final remark is that we can also think about like how we're gonna use this kind of some representations of the 3D rotations in the some neural net tasks. So this is not the machine learning or the deep learning courses, but there can be actually many kind of some graphics related applications that you might need to utilize some kind of neural net, which is predicting some sort of the 3D rotations, right? Then actually, as you can see, there are multiple ways to basically make the neural net to predict some parameters of the 3D rotations. We can use the axis angle representation or Euler angles or the quaternions, even having the 3 by 3 matrix, right? So which representation is the best? So there can be lots of kind of the some kind of the ways that we can make some kind of neural net predicting 3D rotations, and which representation would be the best for those kind of tasks would be kind of the interesting question. So if you're also interested in those kind of things, I also recommend you to check out this paper that also I posted on the Slack. So this paper is also discussing some kind of some details about which representation is the best for this neural net prediction with 3D rotations. Lots of the interesting things. Any questions? So this was kind of the quick overview of some kind of some essential things about some rasterization and some 3D rotation kind of things. And I hope that this will be kind of be useful for many kind of the other so when you implement some kind of graphics applications, and also especially for the neural rendering the contest that we are going to do at the end of the course. And we are, as I said, we are not going to have the lecture this Wednesday, and we're going to resume all the lectures next Monday. We're starting to discuss some of the ideas for the ray tracing. And if you have any questions on those kind of things, please leave your questions on this Slack, and I will also go over your questions and follow up with that. Okay. Yeah. Thank you. Bye.